Hello, this is Steve Sanangelo from the SRS Rock Report with a very exciting interview today. I've been going to have Dr. Louis Arnoux explain what's the nGeni new technology class that's inside the GreenBox. And now, if you remember, we did the interview a few weeks ago with Dr. Louis Arnoux about the thermodynamic oil collapse. And this is his solution how to tap into all that inefficient energy waste. So, Dr. Louis Arnoux, it's nice to have you join us today.
Thank you, Steve. I'm delighted too, and very grateful for the opportunity to explain what's the nGeni GreenBox, how it works, and later on, maybe we will look at what we do with it. So here on screen, you see a simple GreenBox intended to be about the size of a washing machine for home use to provide all the energy requirements of home. There will be other versions for much larger for factories, for schools, for hospitals, and different forms for putting into vehicles and cars, trucks, and so on. And also for shipping, maritime applications, and also later on air applications. So today we are going to look at the GreenBox in the most simple terms. Don't worry about the detail of that slide. We will explain how it works in a minute.
All right, Dr. Louis, I know the biggest problem we're facing is the energy cliff. That's going to be the fossil fuel energy cliff if we don't make any changes. And the solutions that are being offered, whether it's wind or solar or geothermal, they're basically fossil fuel derivatives, and they really don't aren't a game changer. And that's due to the inefficient energy system. So I'm going to let you take over the presentation to explain what the nGeni GreenBox and the new technology class is all about.
Thank you, Steve. So let's move to the next slide, how it works. And as a reminder from the previous interview, let's recall what Einstein was saying is that we can't solve problems using the same kind of thinking we used when we created them. So the GreenBox is based on new principles, still fully in keeping with thermodynamics, however, looking at it in a different way. And the point of the GreenBox is to provide building blocks as well as methods and tools to achieve a transition from fossil fuels to eventually 100% solar. And in doing so, creating new supply chain and opening the door for renewed prosperity. The ultimate aim is to link up the green boxes to form what we call the cool planet Internet of Energy. So let's see. First, as a reminder, to understand how the green box works and why it is designed that way, let's recap on understanding the core problem we face, which is not only the energy climate emergency, but also the matter of supply depletion of resources concerning oil and fossil fuels. So here that diagram, the increase on primary energy consumption for over 2 centuries since the beginning of the Industrial Revolution. You can see that it really took off in the 1950s, and we are now way up at the top here in 2020. Now, what I've done is to superimpose on that chart the amount of energy which is really useful to us. What we usually show in that chart, the work we derive for use purpose is the sliver down and bottom of the chart showing it, and that is about 12% on the this is exactly the reverse of what life on Earth does. Life makes productive use of over 80% of the solar energy reaching the planet. And if we had followed, imitated what life does, we would not have greenhouse gases and the climate crisis, and we would have far more energy available for everybody. The blue sliver on that slide is the amount of energy wastage we would have if we had imitated life, how ecosystem functions. So you can see the difference between the top of that chart, way up there, and what we would have in terms of productive use of energy and energy wastage. Most of the energy on that chart is wasted. So we are up there at 19 terawatt year of primary energy, operating at 12% efficiency. And what we need to do is to go back down to only about 2.7 terawatt years, so less than 3 terawatt years, if we can operate at high energy efficiency, something around 85%. The challenge is how to go down from the enormously wasteful use of energy we have now to an efficient use of energy. And we can't do this with the current technologies we have. We can't do it with the fossil fuel using technology, and we can't do it either with the photovoltaics or wind turbines, as Steve was reminding us a minute ago. So us here, 40W, we have found how to do this, how to very quickly drop from 19 terawatt to less than 3 terawatt years, but retaining the same level of comfort, the same capabilities as we have now. And before detailing how the box works, let's see things in perspective. Here we see a little picture of the planet, and the size is in proportion of what people estimate to be the future energy requirements, about 28 terawatt year per year in 2050. By comparison, the green spot there shows the amount of so-called renewable resources from wind, biomass, hydro, etc. And that circle there showed the size of total fossil and nuclear reserves, knowing that these can only be used once. They are not renewable. So the little green dot above that shows it's what is available, but as we just said, it's not viable with the current technology. We can't really get out of trouble with wind or photovoltaics and so on. And here we have the total amount of energy from the sun reaching the earth every year. So the point of that slide is to show that energy is abundant. There is no energy scarcity, really. Simply the problem is how to access it. We can't access it with existing technology. We need a new technology class. And what we have done is to develop that class, which we called the nGeni. So to reinforce that point, let's look at the internal combustion engine. Here we have a view of a BMW engine, 8 cylinders. You can see all the main parts. It's beautiful engineering. It's very complicated, and it has low efficiency, high cost in terms of buying the machine, and high cost of maintenance and operation. The on-road efficiency is about 20%. And here we get a gas turbine. That one is for a plane, a jet engine. Again, it's beautiful engineering. It's also low efficiency, especially at small scale. It's costly, to operate and maintain, and it's also highly polluting. You can see that if the turbines are big, the efficiency is in the order of 35%. If we go down in scale, it goes down to 10%. At low scale, like a turbine that could be used to supply a home, we're down to 5%. It's not viable. What we have done is to abandon all of that and look at the problem entirely differently. And in our GreenBox, the core mechanical module which provides the power has only 6 moving parts. You can see the contrast, 6 moving parts against all of its complexity in existing technology. So let's look at the first principle of a GreenBox. As I was just saying, large installations like a central power plant or a large gas turbine powering a jet plane is more efficient, but at one point we have far too much waste heat which we cannot recycle. If we have, let's say, a central power station of 500 megawatt at 50% efficiency, we are going to have 500 megawatt of waste heat at one point, and that's far too much in most cases to recycle the waste heat. So we have to move to the point of use or close to the point of use to be able to minimize unused waste heat. And the only way to do that is to go down to the size of what is required at the point of use. If it is a home, it's going to be 3 kilowatt, 10 kilowatt maybe, but not much more. Not megawatts, not hundreds of megawatts. So at the point of use, we have to think small and recycle waste heat. And the only way to do that is by cascading the energy flows. So here we have a diagram. This is how engineers think. So bear with me. On the left, we have low entropy, high entropy. Most people are not familiar with what entropy means. It's an engineering concept. It means effectively a measure of the energy wastage. And typically when we convert energy to derive work to have something useful out of it, we go from low entropy, low wastage, highly concentrated energy form, for example, gasoline or diesel or jet fuel, to high entropy, in other terms, combustion gases, waste heat. So we go from the top down to the bottom and from the left to the right through a series of conversion to supply on the right of the diagram what end users require. So we start from primary energy input with highly concentrated energy, and eventually we will end up with energy losses at the bottom. The GreenBox comprises 2 parts, a primary energy side for the initial energy conversions, and a second side, the end use side, for essentially the energy recycling. In the primary energy side, we convert the energy input into high temperature heat by having the right type of fuel combustions or using concentrated solar. We convert that heat into motive power through a mechanical device. And then we convert that motive power into electricity through generation, usually variable speed generator. Then we recycle waste heat to high temperature, for example, for baking, and to low temperature, for example, for air conditioning, refrigeration, or freezing. And as you can see, between the GreenBox primary energy side and the end user side, we recycle the waste heat at each point of the cascading. Out of that, we get a number of energy flows, motive power, for example, for powering machinery or a vehicle, electricity flows, high temperature flows, and low temperature flows. And eventually, there is always some form of energy losses, we eliminate those losses to the environment. So these are the first principle. At the point of use, at a small scale, we cascade energy and recycle waste heat on and on and on as much as we can. The second principle is to figure out how to do this, what is known as a thermodynamic cycle, what is the best choice of thermodynamic cycle to do this energy cascading, and particularly the first conversion of the heat flow. Here we have a diagram, so bear with me. It's an engineering diagram. It's from Sandia National Lab in the US. Effectively, when one wants to do energy conversion, what matters is the temperature differential between the hot side of the device and the cool side. So here is in degrees C, and we can see we can move from 300 degrees C, medium temperature heat, to very high temperature, 1000, 1200, all the way to 1400 degrees C. And you can see that as the temperature increases, the efficiency of the various systems can increase. There is a theoretical limit. That limit is never achieved. The blue line here provides an indication of what is achievable in practice. And here I've circled in green the kind of area we can use, temperatures area between around 600 degrees C and 900 for converting biomass. And you can see that at that temperature range, with a Brayton Ericsson cycle, we can achieve slightly above 50% efficiency. That's better than in a car, for example, which only achieve about 20%, below down here outside the screen. And if we increase the temperature, then we can move to the right in that area circled in red, where we will be very close to 60% efficiency. This is what we can do with fossil fuels like burning gasoline or natural gas, or concentrated solar. And obviously, the preference eventually is to do it in the solar version. Now, once we've chosen the thermodynamic cycle, what machinery are we going to use? We have seen before that internal combustion engines are not efficient, especially at small sizes, and gas turbines are not efficient either, they are even worse. So we are going to effectively use something else. First, we are going to use external combustion, because if we use external combustion, we can control the combustion and minimize pollutants like particulates. In a cylinder of an internal combustion engine, the pressure, the temperature, the volume keep changing all the time by the millisecond. It's impossible to really fully control the combustion and minimize pollution. In an external burner, it's quasi-steady state most of the time. We can control and really bring down all pollution parameters. So we are not going to use internal combustion in most instances, and we are not going to use pistons or turbines. As you can see on the left of the screen here, we have a screw machine. This is an antique. It was made in 1936 in Sweden. And here we see diagrams from Swedish patent of a Brayton cycle application of screw machines, which were developed initially in 1957 using steel, so steel screws, and then improving that in the early 60s up to 1967, an expander, which is part of the Brayton cycle, using ceramic screws. Now, the proof of concept of that approach, which is neither a piston nor a gas turbine, was successful. It was very difficult at the time to mastermind that because we didn't have at the time the machineries which are available now. So what we are doing is generating new intellectual property, new IP, to bring this technology into the 21st century. It was a technology, in my view, which was ahead of its time. It was quickly forgotten. It was an engineering curiosity because at the time, after the war, the Second World War, the focus was on large power stations, the bigger the better, using steam and gas turbines. So the people who invented that were not able really to commercialize it. They could make money using screw machines for refrigerations, for air compression, and so on. So they did that, and that was parked aside and quickly forgotten. We are reviving it. It was impressive. They managed to operate these devices at 1,200 degrees C, initially with steel screws. Normally, the steel should have melted, so they had clever design, and I know what they were. And then they moved to ceramics. Effectively, what we are doing is going beyond what is known as combined heat and power. CHP has been around for a good 40 years, but it has a limited efficiency. The typical maximum efficiency for electrical power generation is 35%. We can go well above that. Turbines also are very inefficient, as I said. We can achieve above 55, around 55 efficiency in the 3 to 1 megawatt, 3 kilowatt to 1 megawatt range at the point of use, which is really unprecedented. So how do we put all that together? And Brayton Ericsson system operating with screw machines instead of pistons or turbines. So in all Brayton Ericsson systems, we have a compressor and an expander. It could be a turbine, but we don't do that. Because we go to small sizes, we use screw machines. And then these compressor and expander are connected together with a shaft, and the shaft can link up with a power generator to generate electricity or powering a vehicle's powertrain. Around that, we have a number of other components, a burner or a solar receiver for the primary energy input, a primary heater, which is a heat exchanger, and a recuperator, which is also another kind of heat exchanger to recycle waste heat. So we put fuel in the burner, we generate a high temperature. That hot flow of hot gases goes through the primary heater and then to the exhaust. At the other side, we have an air intake through the compressor. The air is compressed, goes to the recuperator where it is reheated with the waste heat. We are going to see that in a minute. The warm air, warm compressed air goes through the primary heater where it gets to very high temperature. As it gets to high temperature at constant pressure, the volume of the air expands enormously, and that increased volume of hot air, compressed air, goes to the expander. As it expands, it transforms its energy into mechanical power. It rotates the expander, and the gases, the air, cool off. So we have a cooler flow going to the recuperator, but there is still some heat in there. So this is why we have a recuperator to recycle that waste heat and pre-warm the cold air coming in. And then we have the exhaust at the end. So it's engineering. It might sound a bit complicated to some people in the audience, but this is in essence how it works. The interview is being recorded, so you can revisit it, replay it to understand better in your own time. An important point is the pressure is only around 2 to 4 bar. Bar is a unit of pressure. Other units are PSI, pascals, and so on. 2 to 4 bar is the sort of pressure you have in the tires of transport vehicles, cars, or trucks, versus over 200 bars in current efforts to use critical CO2 in Brayton system using gas turbine on a large scale. So you can see we go small, we go simple, and also safe. 200 bar is very high pressure. 2 to 4 bar is very common and not dangerous. The fact that we are using an external combustion means that it's fuel agnostic. We can use any kind of fuel. It can be fossil fuel like oil, gasoline, diesel, jet fuel, or it can be biomass like bio oils, or biomethane. It can be natural gas. It can be recycled processed heat or direct concentrated solar influx. Only the primary input, the burner or the receiver changes, but the rest of the equipment remains the same. So we have a high flexibility, and customers can shift from one fuel to the next if their circumstances change or if the price change. It's easy to do. We have a very high temperature differential operating preferably from 1000 to 1400 degrees C, which is the main reason why we can have very high efficiency. Now, another interesting feature is what we call the torque curve or the efficiency curve. People and car enthusiasts will be familiar with what a torque curve is. It's the amount of power you can get to the wheel to power your car, in simplified terms. In a diesel engine or in a gasoline engine in a car, for example, or a truck, that curve has a peak. It goes up, reaches an optimum point, and then goes down very steep. This is why you have complex gearboxes to try and keep operating the engine at the optimal point. With a screw machine, the curve is very flat. So it's more like shoulders and a flat plateau in between two shoulders, which means that you can vary the RPMs from low to very high without losing in efficiency, which means, for example, for transport applications, a much reduced gearbox, much simplified gearbox, and also high efficiency because you only use the fuel you really need. If you don't need much power, you reduce the use of fuel, you power down, but the efficiency is still high. So this combination of features enable us to achieve above 55% motive power or electrical efficiency directly at the point of use. Again, this is unprecedented. We don't know anybody else who could achieve that with other technologies. And we can therefore combine this with what is called a heat pump. A heat pump is what we have in the fridge, in the freezer, or an air conditioning unit to recycle the heat, which is still in the exhaust on that diagram at the top and at the bottom, and make use of that in, for example, to provide hot water, air conditioning, refrigeration, and even freezing. With that approach, we can do easily minus 80 degrees C, which is very low. The building blocks to do that are available. We are not so-called reinventing the wheel. There is high temperature piping. This picture there on the top left-hand corner is from aerospace technology, is from the Ariane European rocket. Next on the right, we have twin screw compressor. This is a Whipple compressor used as a turbocharger to improve the efficiency of car engines. On the right, we have a hand holding a sample of an advanced ceramic heat exchanger. That sort of exchanger can be produced very cheaply. For a home, the heat exchanger will cost about 50 euros or $50 US. Here you can see the twin screws. This is how it looks like, a modern twin screw, similar to what's in the compressor or in the expander. In terms of solar application, there is a range of parabolic solar concentrator, which can be used at home in an urban environment. This one has been made in China. It can be available for about 100 euro. Obviously, our solar concentrator would be a bit more sophisticated than that, but I re-emphasize the point, it can be made at very low cost. Here also we have a variable speed power generator. This one can operate up to 15,000 RPM. It's very efficient and very compact. And we have an example of a wireless remote management module. The idea is that the GreenBox will be remotely managed. End users are not that keen normally to transform themselves into power station operators. We intend to manage the systems remotely for them and network the boxes, and eventually this is how we will generate or deploy the Cool Planet Internet of Energy. So let's review now in summarized form what the GreenBox does. A GreenBox, which is modular, it can be reconfigured as if, for example, the end user needs more input or different kind of input. The GreenBox can be upgraded to meet the requirements. We estimate that in terms of mass production of those boxes, we can achieve less than 500 euros per kilowatt installed. Typically, current prices, current cost are more in the order of 2,000 per kilowatt installed. So we can achieve much substantial cost reductions for the equipment and for the energy made available, typically 4 cents per kilowatt hour or less. At the point of use in the OECD for domestic applications, currently the average price for electricity is around 20 cents. So we can move down from 20 cents to around 4 cents. It's interesting. And the idea is to share the savings, which corresponds to the energy wastage we are retrieving that way. We can share it between the end users and the supplier of the technology. So that GreenBox can indifferently use fuels, fossil fuels or biomass. We can use the sun as concentrated solar with a parabolic concentrator, or recycling waste heat, for example, in industrial processes. I know a lot of instances where heat at 500 or even 800 degrees C is rejected to the atmosphere. It's a waste, and we can recycle that. So it shows that on the primary energy side, there is a very high flexibility. And what comes out of the other end is also flexible. We can produce all the kinds of energy flow an end user may require. Motive power, electricity, process heat, for example, baking, hot water, cold water, air conditioning, refrigeration, and freezing. And again, as I said, the device can be managed remotely through advanced broadband communication. We have our own IP about that. An important feature is that those various energy flows can be varied in real time independently from each other. So if, for example, at one point, the end user requires more electricity and less heat, that can be done. Or the reverse, for example, between winter and summer, the heat requirements will be less in the summer, more air conditioning, more cooling, variation of electricity demand between during the day and less at night. The GreenBox is structured to be able to match by the millisecond the end user requirements as they change. In addition, we have our own IP, our own intellectual property for very low cost energy storage, which is important, especially for solar application. We can store enough energy for operating for a week or even a fortnight, for example, in winter when there is not much sun because the sky is cloudy. We can also recycle water because we have very low cost pressure inside the GreenBox. We can add modules like reverse osmosis to transform grey water into recycled fresh water. And we can also retrieve carbon dioxide from the atmosphere. The GreenBoxes operate by breathing in air, compressing it, heating it, and rejecting it. So since we are breathing air, we might as well capture the CO2 in the air and therefore contribute to cooling the planet. It's an additional module using proprietary technology to absorb the CO2 and recycle it as liquefied CO2, which is a commercial product, so it's a byproduct of the GreenBox. So as you can see, the GreenBox is a very flexible device at the point of use with much significantly lower cost than what is currently on the market. It can accept any kind of energy input, and it can produce the whole variety of energy output required by end users, as well as contributing to keeping the planet cool, storing energy, and recycling water. Now, part of the objective, as I said, is to network the GreenBoxes, because a GreenBox at somebody's place at home may not have much use, say in the afternoon when everybody's at work or at school, but it can export, for example, electricity through the grid to in where electricity is required, like in the factory or in the shop or in the school or in a hospital. So effectively, the point is to have GreenBoxes networked and installed everywhere where its energy is required. So here, for example, we have a shopping mall with supermarkets, and we have little schematic GreenBoxes on the rooftops, receiving energy from the sun, providing energy to the supermarket. At the same time, in CO2, selling that obviously as liquefied CO2. We have factory doing the same thing. We have homes with connections to the electricity grid. So they can exchange electricity, they can draw electricity from the grid or contribute to the grid, which means that the grid is transformed into an energy bank. You deposit electrons or you withdraw electrons constantly from multiple point of views and generation. And we can also install a different kind of GreenBox, a simplified version in cars, in trucks, and those cars can also be networked through broadband, which also contribute to the operation of the system. The cars can be connected when they are not in use, connected to the grid by the stationary GreenBox. So it gives you an idea of how the system can expand in a very flexible way and substantially contribute to keeping the planet cool by extracting back from the atmosphere the excess CO2. So the nGeni is a new technology class. Its aim is to retrieve a substantial part of the about well over 5 trillion euros or dollars per year currently lost as energy wastage. Doing this will return much more than what is required currently to re-engineer the entire energy, transport, communication, and global food chain, and also other production chains, to achieve in record time 100% a solar-based, prosperous sustainability for all stakeholders globally. Our aim is that it should be beneficial, it should be rewarding, including financially, for all stakeholders. Accessing those funds requires doing 10 times more with 10 times less in energy terms, 100% solar-based, and that is what a new technology class, the nGeni, enables to do. So thank you very much for that, Steve. I'm now passing back the microphone to you.
All right, well, thank you very much for explaining that, Dr. Louis Arnoux. I know it's a little bit complex. We will do some follow-up interviews. We could do some follow-up interviews explaining some of this more in basic terms for those who don't quite understand all the detailed engineering. But it's useful for those who are engineers who think in engineering terms. But again, we will provide some follow-up videos on why the nGeni or the technology class is a viable solution compared to either wind or solar, geothermal. All the different solutions that they're providing now are attaching themselves to a very inefficient system, energy system, which is only 12% efficient. And then we have to remember the wind and solar and geothermal, they're all constructed from fossil fuels. And so the interesting thing about the nGeni, as you mentioned, it's very low tech. It's more low tech. It's not high tech. It's not complex. And the components in the GreenBox are very easily, they're very abundant and they're very low cost. And I think that's a much better solution or alternative to the highly complex wind and solar that, and you say your concentrated solar that's the way to go. And you're talking about a very efficient solar. What we have now with the photovoltaics is very inefficient solar. And so I wanted to thank you very much for all the people watching this video. And again, please look out for new interviews with Dr. Louis Arnoux explaining some of these different, comparing nGeni to other solutions that are not going to work. And if you want to contact Dr. Louis Arnoux, would you let them know how they can contact you?
Yes, thank you, Steve. Thank you very much again for this opportunity to explain. Again, I apologize for the engineering terminology and so on. As Steve explained, we will show subsequently how it can be used in the car, in the trucks, in the plane, on a boat, and at home, or in a factory, or in a supermarket. So you will see the applications, and it will become, I guess, or I hope, a lot clearer. You can join me by contacting me at Louis, L-O-U-I-S, at Fourth Transition Wealth, all in one word, .com. So fourthtransitionwealth.com. Quite a few people contacted me after the first interview. I was delighted to receive their comments and provide additional explanations. So everybody is welcome. Thank you very much.
All right, now I will also provide a link to be able to contact you as well. Well, thank you very much for your time, Dr. Arnoux, and we will again be providing some shorter updates, shorter presentations in the future.
Thank you very much. Thank you, Steve.
Thank you.